Wayne. Hi, Travis. This is John Whitaker for the Probability Graduate Level class, and this is our 17th video lecture. And this is the last lecture that covers material that will be on Test 1. And today, the main thing we want to do is the central limit theorem. And it has to do with a type of convergence called distribution. And let's go ahead and get started with that. First of all, I'm going to describe a definition of what it means to converge a distribution. So it says this sequence of random variables x of 1, x of 2, x of 3, forever, converges in distribution to a random variable x if the limit as n goes to infinity of f sub x sub n of a equals to f sub x of a, where f sub x sub n of a is the CDF of x sub n, and f sub x of a is the cumulative distribution function of x. So their distributions converge. And we think of this as pointwise convergence for the distributions. Well, with that having been said, we're ready to state and prove the central limit theorem. And as I go to state and prove it, I want to tell you that this central limit theorem, along with the strong law of large numbers, which of course has to do with almost sure convergence of a sequence of identically distributed random variables. If you do it a bunch of times, the experiments a bunch of times, essentially is what that random variables represent, and divide by the number of times you do it, you ought to get the average. And that's what the strong law of large numbers says. Well, the central limit theorem and the strong law of large numbers are probably the two most important facts, well-known facts from probability. Okay, here's the central limit theorem. Okay, so it says let x1, x2, forever be a sequence of independent and identically distributed random variables having, each having finite mean, mu, and finite variance. So the mu, I should have said this, that's equal to the expected value of x of I. Finite variance variance of x of I equals sigma squared. Then the distribution, or then, let's just say it this way, this particular function, I'll say then the distribution. X of 1 plus x of 2 plus all the way up to x of n minus n mu over the square root of n times sigma converges to the distribution of the standard normal random variable. It's an amazing fact. Okay? You look at this type of random variable, which is a combination of n independent and identically distributed random variable, and they become, in some sense, like the standard normal random variable. But let's give a little bit more explanation what this means, and then let's do the proof. And we'll do one example, and that'll be it for this lecture. Okay. So, in other words, what we have is the probability, I should say this, the limit as n goes to infinity of the probability that x of 1 plus x of 2 plus x of n minus n mu over n square root of n times sigma. Okay. That being less than or equal to a equals, or that quantity converges to 1 over the square root of 2 pi integral from minus infinity to a of e to the minus z squared over 2 dz. Okay. That's what we have. That's true for any a. Okay, let's look at the proof. So let's let x of 1, x of 2, and forever be a sequence of independent, identically distributed random variables. Okay. So that's what we'll start with. And this proof is going to be dependent upon a lemma, which I'm now going to state. Okay? So this lemma I'm not going to prove, it's just something that we'll use. Before I leave that at the board, let's write down just each having finite mean, expected value of x of I, equal mu, and finite variance the variance of x of I equal sigma squared. Okay, so the lemma that we use here says the following. It says, let z sub 1, z sub 2, forever, up to z sub n and beyond, okay, be a sequence of random variables whose CDFs, so cumulative distribution functions, are denoted by f sub z n, or f sub zi, zn, all right, of t, and whose moment generating functions are, so here's the way I denote them. They're phi sub zn of t. Okay. We're going to let z be a random variable. Whose CDF is f sub z of t, and moment generating function is phi sub z of t. If the moment generating functions, so let's say they converge. So if phi this sub z sub n of t converge, and we're thinking pointwise here, to phi sub z of t. So if the moment generating functions for the sequence of random variables converge to the moment generating function t, then f sub zn of t converges to f sub z of t. There's a little bit more to be written there. It's for all t where f sub z of t is continuous. I should say for all t where t is continuous. So we're going to use this lemma, right, to prove the central limit theorem. So we have the hypothesis, the conditions for the central limit theorem. We have this lemma we're going to be able to use, even though we haven't proved this lemma. So we're going to break the central limit theorem into cases. So case 1 is where mu equals to 0 and sigma squared equals to 1, sigma equals to 1. And so here, in using this lemma that we just wrote, the way that we're going to show that that particular random variable that we had listed converges in distribution to the standard normal, we're going to show that the moment generating functions for that random variable that's mentioned in the central limit theorem converges to the moment generating function for the standard normal. What was the moment generating function for the standard normal? Wasn't it e to the t squared over 2, I think? So here, we'll start off by noting the moment generating function of any one of the x sub I over the square root n. So this is just some small piece of the function in the central limit theorem that we want to show its distribution goes to the distribution of the distribution of the standard on. One little part of it. Note the moment generated function for this guy is phi, so x sub I over square root n of t, and that's going to be equal to the expected value of e I times the square root of I over square root of n. It wouldn't be I, it would be t. Okay? So, the moment generated function of, now in this case where mu is 0 and sigma squared is 1, the random variable involved in the central limit there becomes, remember it's that x sub i's added together up to x sub n minus n times mu, but mu is 0, over the square root of n, well, that's still there, times sigma, which is 1. So here, the moment generated function of this, the sum as I runs from 1 to n, of x sub I over the square root of n, that's the function involved, is, well, it would be the expected value of e t times the sum as I runs from 1 to n of x sub I over the square root of n, which would be, if I expand this, is the expected value of e times t of x sub 1 plus x sub 2, each one of the square root of n, plus we'll keep going all the way up to x sub n over the square root of n. And then if I distribute that t, that's equal to the expected value of e of t xi over the square root of n, it should be x1, plus t x2 over the square root of n, and we'll keep going, plus t xn over the square root of n. That's the expected value of e, well, you can break this expected value of expected value of e raised to a power that is a sum as the expected value of the product of e raised to each power is involved in the sum. This should be x1, et x of 2 over the square root of n times e t x of n over the square root of n. Now, due to independence, this is the same thing of x of I as e t x of I over the square root of n, it's e to that, times the expected value of e, excuse me, x of 1, t x of 2 over the square root of n, times, we keep going all the way to the expected value of e raised to the t x of n over the square root of n. Now, since they're all identically distributed, the expected value of e to the t x of 1 over the square root of n is the same thing as the expected value of e times t to the x of 2 over the square root of n. So I'll rewrite this as nothing more than the expected value of just one of them, expected value of e t sub x of 1 over the square root of n. But that's nothing more than phi of x times or over x of 1 over the square root of n. Okay, that's what that is. Of t, the moment generating function. Wait a minute, I made a mistake. That's this guy raised to the nth power because there were n of them. So it's this guy raised to the nth power. Okay. So that's what we want, what we have. All right. So we want to show well, another way of looking at this, I'll write this one more step. With this is equal to phi, if you look back here, it's really phi of x sub I of t over the square root of n. Okay? And I'll write down x sub 1 raised to the nth power. So what we want to do in using the lemma to get the result of the central limit. So we want to show that the limit as n goes to infinity of phi sub xi of t over the square root of n raised to the nth power of this quantity equals to, this is the moment generating function, the moment generating function for the standard normal, which was e to the t squared over 2. That's what we want to show. Happens. So here, let's note that the limit as n goes to infinity of phi sub x sub 1 of t over the square root of n raised to the nth power. Okay. So as n gets really huge, t over really huge numbers go to 0. So this is the moment generating function evaluated at 0. That's the 0th derivative. Okay. Evaluated at 0. That's supposed to be e, the expected value, of x to the 0. Well, the expected value of x to 0 is 1. So the expected value of 1 is 1. So this tends to 1 raised to the infinity. Okay? That's an indeterminate limit form. And so what we do is we consider, in order to get ourselves into the L'Hopital's rule situation, we consider the limit as n goes to infinity Ln of this quantity. And that allows us to bring that n down. So I'll say that. Note, the limit as n goes to infinity Ln of phi x sub I of t over the square root of n raised to n is equal to n times, well, I forgot the limit. The limit as n goes to infinity of phi, bring down the n, ln of phi sub x sub I t over the square root of n. Now, as n goes to infinity, this becomes an indeterminate limit form as infinity times 0. So what I do is I pull this n to the bottom. So as the limit as n goes to infinity of ln of phi of x sub I of t over the square root of n all over n to the minus 1 over n. That's the same thing. All right. This is now a 0 over 0 situation. And we can use L'Hopital rule. So I take the derivative top over the derivative bottom. So this is equal to the limit as n goes to infinity. Now, the derivative of the top, the derivative Ln of something, is 1 over something. Times the derivative of something. So I take the derivative of this guy, so that's phi sub x sub I, it's derivative, prime, evaluated t over the square root of n. Okay? And then we have, by the chain rule, take the derivative of this. Now we're taking the derivative with respect to n. So just over here, this is t n to the minus 1/2 is a one way of writing t over the square root of n. Okay? So I'm going to take its derivative, which would be t, that's the constant. Then I write down minus 1/2 n to the minus 3/2. So that's the top. Okay. The derivative of the bottom will be minus 1 n to the minus 2. Okay, let's look at that for a second. Here again is phi of 0, that's just 1. When n goes to infinity, this goes to 0. The derivative evaluated at 0 is just the expected value of x. This guy can be pulled up here to the bottom, if you will, and we get into the minus 1/2. And when we would do that, what we end up getting in the minus 1/2, that's what we have here, would be 0 on the bottom, 0 in the top as well, because this guy be going to 0. So here, I'll rewrite this. As, if you will, so this is a 0 over 0 form. That's what we are. So I'm going to use L'Hopital's rule again, but before I do, let me rewrite it. The limit as n goes to infinity. The way I'll rewrite this is the first derivative of x of 1, not I. I've written i's. It should be 1. Okay? Let's go back here. Make this change. Here, I got excited. These are x of 1s. Sorry. What I've argued is this is 0 over 0 form. So make those changes. I'm going to rewrite it so I see that it's 0 over 0 form a little better. So it's first derivative evaluated at t over the square root of n. Here's a t. There's a minus 1/2 and minus 1 at the bottom. They're going to cancel just to make 1/2. The n to the 3/2 I'm going to pull to the bottom. There's also a phi of x of 1 of t over the square root of n. And then there's this n. There would be a 2 here. And then there would be an n to the minus 1/2. That's what we are. Okay? And this again I said was a 0 over 0 form. So we use L'Hopital's rule. So this is equal to, so I take the derivative of the top. The derivative of the top, and so t is a constant, so I'll just write it down. How I take the derivative? The derivative is second. x of 1, I have t square root of n. I take the derivative of this. Again, this was t times n to the minus 1/2. So I write out minus 1/2. Then we have t times n to the minus 3/2. That's what we're looking at. All over the bottom, we have some function right here times another function, each of which has n involved. And so I'm to use the product. So I write down I write down the first guy. 2 times phi of x of 1 of t times square root of n. So that's the first guy. Now I take the derivative of the second guy. So that'd be minus 1/2 n to the minus 3/2. Plus, now I write down the second guy. So that's n to the minus 1/2. And then the derivative, there's a 2, so I'll write it down. There's a derivative. There is a derivative of this function, which is going to be the first derivative of x of 1. and it would be t times square root of n, t over square root of n, and then this would again be t, call it 1/2. So it would be minus 1/2. T n to the minus 3/2. Okay. This n to the minus 1/2 here, the minus 1/2, minus 1/2 n to the minus 3/2, they cancel. So I'm going to rewrite this as limit as n goes to infinity. T, the second derivative, this part and this part, so I've got a t squared. Oh, that's good. I got a t squared. That's excellent because that's in the moment generating function for the standard moment. So that's what this part is when these have been canceled. And in the bottom, I still got this 2. This is gone. And then plus, here, this part's gone, so I still have a t. I've got 2 n to the minus 1/2. Okay. This is phi prime x sub 1 of t over square root of n. Okay. And then there is this t I've already accounted for. This 2 I've accounted for. Okay. So that's where this t to the n minus 1 comes in. This guy's canceling right here. Just like that. That's what it is. Okay. Now, as t goes to infinity, we're curious what this looks like. So, sorry, not as t, but as n goes to infinity. So t squared is a constant. The second derivative of the moment generating function evaluated, well, this is going to 0. So that's really the expected value of x squared. Well, in our case, remember the variance is equal to 1. And the variance, so I'll write this down, since the variance of x sub 1 equals to the expected value of x sub 1 squared minus the expected value of x sub 1 to be squared. And in this case, this is 0. Then the variance of x sub 1 is equal to the expected value of x sub 1 to be squared, because this is 0. So this says, remember the variance of x sub 1 was sigma squared, is equal to the expected value of x sub 1. But what was sigma squared? That was 1. Okay? X sub 1 squared. So here, this part right here is tending to the second derivative of the moment generating function evaluated at 0, but in this case, that's just going to be 1. That's what I want. Okay, so that limit, you know what, I should explain a little bit more before I move on. Excuse me. So from where I am, this part is going to go to 1. This is just t squared. This part, as n goes to infinity, will go to the moment generating function evaluated 0, set with 1. This is going to go to 2. Here, this part goes to the expected value of x, which we know is 0, and this is over the square root of n, which goes to infinity. So it's 0 over something going to infinity. That goes to 0. So this whole thing goes to 0. So what we end up getting, I can write down the answer. This is equal to t squared over 2. Okay, that's my explanation. Now, remember, we took ln of our problem. So, what we know is that the limit of n goes to infinity of phi sub x sub 1 of t over square root of n raised to the nth power. That's equal to e t squared over 2. Okay? E raised to this. And that proves the case we're going to the central limit theorem in case 1. Now, in case 2, is if mu is different from 0 or sigma squared is different from 1, then we're going to consider the random variables x sub I star equaling to, so it's x sub I minus mu over sigma. And let's take a look at the expected value of the x sub I stars. Well, that's equal to the expected value of the x sub I minus mu over sigma. The sigma in the bottom can be pulled out, and then it's the expected value of x sub I minus mu, which equals to 1 over sigma. Here's the expected value of x sub I minus the expected value of mu. And of course, the expected value of x sub I is equal to mu, so this is equal to 1 over sigma times mu minus mu, which equals to 0. So the expected value of the x sub I stars is 0. Now let's talk about the variance. The variance of x sub I star, well, that's equal to the variance of x sub I minus mu over sigma. So we'll take mu. That's equal to the expected value by formula of x sub I minus mu, over sigma to be squared, minus the expected value of x sub I minus mu over sigma, which, and all that to be squared, which we found that to be 0 already. So this is equal to just this part, which is the expected value of x sub I squared minus 2x sub I mu plus mu squared. You know, I should leave it like it is. No, let's write it down. X sub I squared minus 2 times x sub I mu plus mu squared over sigma squared. I don't like that. I'm sorry. Let us rewrite it 1 second. It's this way. It's x sub I minus mu. I can do what I was doing before. It's much easier to write this. The top being squared over the bottom being squared. It's an expected value. The bottom is a constant, so I pull it out. What that expected value of x sub I minus mu to be squared is, since the expected value of x sub I is mu, this is nothing more than the variance of x sub I. This was a sigma. So this is 1 over sigma squared, and here's the variance of x sub I, which equals to sigma squared. So this is sigma squared over sigma squared, which equals to 1. So, what I want to tell you is that the x sub I stars, then, are independent. They turn out to be independent and identically distributed. Random variables. With expected value of x sub I equaling 0 and variance of x sub I equaling 1. So by case 1, we get to apply case 1 now. case 1, that tells me that the distribution of x of 1 star plus x of 2 star plus all the way up to x of n star over the square root of n converges to the distribution of the standard norm. And so, what is this? This is x of 1 minus mu over sigma plus x of 2 minus mu over sigma plus x of n minus mu over sigma all over the square root of n converges in distribution to the standard norm. Random variable. I was writing a RP here. Random variable. So let's look at what that is. Well, the sigma can be brought down to the bottom for each one of them. And then what we get is x of 1 plus x of 2 plus all the way to x of n minus, there were n number of u's all over the square root of n times sigma. Convergence and distribution. To the standard normal range. Okay. And that is the proof. I want to do one example where we use the central limit theorem. And so, and then we'll call it this. So, 10 fair die are rolled. Says find the approximate probability that the sum of the die roll obtained is between 30 and 40. So let's start off for trying to look at this problem by saying, let's let x of I be outcome of the I die. I guess it should be probably 10 fair dice. I mean, say it's not big deal. 12 dice. Change. It's always good when someone from Alabama is talking about English. Okay. Okay. So here's what we want. We want to find the probability that 30 is less than the sum of the x of i's. Yeah. I don't know what who's less than 4. Approximately. So I want to make this look like the central limit theorem. Okay? To approximate this probability, we will use the central limit theorem. To find. So I'm going to change the problem just a little bit because they can end exactly here. I'm going to use 29.5, and I will tell you to use these numbers if I decide to change it. Less than the sum as I run from 1 to n of x of I. So in a problem, I will tell you what to use here. And let's make this 40.5. Now I want to use the central limit theorem. So here's x1 plus x2 all the way up to xn. That's not doesn't go forever, but it's sort of like it's getting close to the thing that converges the distribution to the standard norm. Okay. It's not quite, but that's just the sum of the first n. We need to minus n times, or n is 10. We need to minus 10 times the expected value. Okay, so I have to find the expected value of x of I. And what I can see is that the x of i's outcomes, they are independent, and they would be identically distributed. So whatever happens on one of the die roll doesn't affect what happens on another one of the die rolls if we roll both of them at the same time. And we'd expect them to have the same probability mass function. It would have the same probability mass function. So note, the expected value of x of I, well, all right, this is a discrete random variable. Remember, x of I is the outcome. It's 1 through 6. One of those. Each one will be equally like it. This will be the sum as, let's say, x runs from 1 to 6. This would be x times f of x. And you can call it x of I, but it matches the variable here. And that's equal to 1 f of 1 plus 2 times f of 2 plus 3 times f of 3 plus 4 times f of 4 plus 5 times f of 5 plus 6 times f of 6. And that's going to be equal to, well, f of anything in this case, the likelihood of getting a particular die roll outcome is 1 out of 6, because everything's equal to 9. So this will be 1 out of 6 times each one of these numbers. So I add up these numbers, 1, 2, 3, 4, 5, 6. There's 15, 18, 20, 21. So 21 out of 6, and that's the same thing 3 goes into that. It's 7 halves. That makes sense. 3.5 is the expected value on the die roll. Yep. Now the variance of an x of I, well, that's the expected value of x of I squared minus the expected value of x of I to b squared, which I just found out. So note, the expected value of x of I squared, that's going to be the sum as x of I again runs from 1 to 6, of x sub I squared times f of x sub I. Again, this is 1/6 every time. And then when I let x sub I be 1 and square it, I'm just going to get 1 plus 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, plus 36. Okay, so that's 41, 61, 67, 77, 86, 90, 91. And so the variance of x sub I is going to be 91 over 6. That's what I got. And then it's minus 7 over 2 to be squared. So that's 91 over 6 minus 49 over 4. What it means, but the 1 through 12. So this is 182 over 12 minus 3 times this. I think it's 147 over 12. That ends up being 35. Okay, so I've erased what we were looking for. So the probability that 2.9 is less than x sub 1 plus x sub 2 plus x sub n is less than 40.5. That's what we're looking at. That's what it's actually looking at. It's 29.5. We're done wrong. That's our problem, to get the approximate that the sum is between 30 and 40. It was 30 and 40, I could have done inclusively, so I guess that's what I meant by this. That's why I want a little lower. So look, I think I miswrote the problem. I should have written it this way. That's what I was looking at. Okay? I didn't write the equal to before. Let's say that's what we're looking at. So I get a little lower than that. All right. So here's what we have. All right. This is part of the random variables involved in the central limit. But what do I need? I need minus n times mu. Okay? So what was n? N is 10. That's how many times we do it. That's what it is, 10. And what is mu? Mu is the mean, which was 7.5. So 10 times 7.5 is 70, which is 35. So what I'm going to have to do is to get 35 involved. And so I'm going to subtract 35. But if I subtract 35 from the middle, to make it look like the quantity that's involved in the central limit theorem, I'm going to have to subtract 35 here. So that's 5.5. And when I subtract 35 here, that's minus 5.5. Okay, that's what we're looking at. Okay, now I need the square root of n times sigma. So here, so this is sigma squared. So here, if I say this is the same thing as the probability. Okay, so here in the middle, I'm x of 1 plus x of 2 plus x of n minus 35 over the square root of 10, and then the square root of that, so we're at 35 over 2. And here, all right, minus 5.5, square root of 10 times 35 over 2, 5.5. Here's the square root of 10 times 35 over 2. This middle now matches exactly what we wanted for the central limit theorem to apply. Almost done. So this is approximated by the standard normal, which I'll say is z. I'll let it be known by z. That number ends up being approximately minus 1.02. Less than, I'll say less than or equal to z, less than or equal to 1.02. And let me back up here. You can change all of these to less than. That's fine. Reading that earlier. Okay? So that's where we are. Now, I haven't done this before, but one of the main things in statistics class, probability class, just touched on probability, is how do we work with the CDF of a standard normally distributed random variable. Well, we can't integrate. There isn't a closed form for that. 1 over square root of 2 pi e to the minus z squared over 2 dz. We don't know the answer for that antiderivative. But we can use computers to approximate what that will be from minus infinity up to a positive number or any other number. And we have charts. And in your book, you have a chart. And it uses some positive numbers there to get some approximation. But it's the CDF is what's involved. So here, what is this? If I want to understand this, this is what I think of. The PDF of the standard normal is this bell-shaped curve. That's that 1 over square root of 2 pi e to the minus z squared over 2. Looks like that. If you want the region that's in between here, this is what you're looking at. What we have charts for are things less than this. So what I'll say is this is equal to, okay, this part, okay, that part, I did the wrong thing. It's this part, back, forever, minus, which I do have in charts. Charts will give me this. This part. But we don't have the negatives listed in charts normally in the book. But due to symmetry, here's what we can say. This is the same thing as this part. Okay. Minus due to symmetry, the part here that's less than 1.02 to the left of it is the same as the part to the right of positive 1.02. So this is equal to this, again, the same part we've been looking at, 1.02 back. Minus, this is 1, minus this part. Okay, I can describe this. This is, well, these are the same. So if you will, I'll say it's 2 times this area. Minus 1. Okay? All right, what is this area? That's nothing more than 2 times phi, where that's the standard normal CDF, evaluated 1.02 minus 1. And that we can see from the chart. And I'll even try to say where it is in our book real quick. Let's see if I can find it. Yes, it's on page 74 of the book that I'm looking at. It's in chapter 2, but in the old version I'm looking at, it's in page 74. But what you find is this number is the same thing as 2 times 0.8461 minus 1. And so our approximate answer is 0.6922. All right. So we rewrote our problem in such a way that the central limit theorem can apply as an approximation. Well, that's enough, gentlemen, for today. Thank you very much.